Section 7.7 continued. Composition of inverse functions. We've worked with composite functions on prior sections. Now we want to look at the composite function of a function and its inverse. So f and f to the negative 1 are inverse functions. Then I have f to the negative 1 of f of x. And I have f of the inverse of f of x. And that states that they always equal x. In other words, what they're saying is, if I put the function of f of x here, and then substitute that value into the inverse, and put the inverse here and substitute that into the function, I always end up with the value of x. What that really is stating is, no matter what value I put in here, for example, -5, I'll get a certain solution. If I put -5 in here, I'll get the same solution in both composite functions. They always have to turn out to equal the same element. So let's take a look at an example. Here I have f of x equals 2x minus 5. I want to find the value of each. I want to find this value. So I need to find the inverse first. So I know how to do that, which is to substitute y for f of x. And for x, I put in an x minus 5. I now switch the values. So y becomes x, and x becomes y. I'm going to add 5 to both sides, so 2y equals x plus 5, and divide by 2. And that's going to give me x plus 5 over 2. Now what I can do is find this value, which would be f of a negative 1 of f of x. So I want to substitute 10 into f of x. When I do that, that's going to give me 2 times 10 minus 5. When I simplify, that's going to give me 20 minus 5, which is 15. I want to put this value into the inverse. So f of a negative 1 of 15 is going to be 15 plus 5 over 2. 15 plus 5 is 20, divided by 2 is 10. To prove what I said on the previous slide, I can now do the other composite function, which would be f of the inverse of x. They didn't ask us to do that, but I'll show that to represent the previous slide. So now I need the inverse of 10, which is going to give me 10 plus 5 is 15 over 2, which is 15 halves. I'm going to use that element in the function, so f of 15 halves. That would equal 2 and 15 halves minus 5. And when I simplify, the 2's cancel, I'm left with 15 minus 5, which is 10. And notice, I end up with the same value. In other words, x. In this example, I'm given a function. I want to find the inverse of that function, the domain and range of f and the inverse of f, and I want to determine whether the inverse is a function. Let's start with the domain of my function. Here, I have to use a lot of information that I've learned in the past. I can rewrite this function as 1/3 x squared. Since I know this is a quadratic, the graph is going to be U-shaped. Nothing is added or subtracted from that term. Therefore, on a graph, this is not going to have a vertical shift up or down. Also, I don't have a set of parentheses with something added to x or subtracted from x, so it's not going to have a left or right shift. So I know the only thing I have to worry about is my 1/3, which is a stretch or a shrink. So I know I'm going to have a U-shaped graph at the origin. Since that's true, I know my domain, or my x values, are x equals all real numbers. My range, or my y values, are y such that y is greater than or equal to 0. Now I have to find my inverse. I can still use this information to determine a lot of information about my inverse, whether it's a function in its domain or range, but I have to find the inverse. To do that algebraically, I'm going to have f of x become y, and that equals x squared over 3. Now I switch my x and y's. That gives me x equals y squared over 3. Multiply by 3 on both sides, I get y squared equals 3x. Take the square root of both sides, I get y equals plus or minus the square root of 3x. From here, I know that this, since it's plus and minus, is going to be reflected over my identity function, and it's going to look something like this. You can also check that on your calculators. From that depiction, I know that it's going to fail the vertical line test. Therefore, this is not a function. And I also know that I can switch the domain and range of the inverse. The x becomes the y's become the x. So my domain, x is greater than or equal to 0. And my range, y equals all real numbers. Again, I'm given a function. I want to find its inverse, and I want to find the domain and range of the function and its inverse, and then I want to determine if the inverse is a function. Let's begin with the domain of our function. For values of x, I can't have a denominator that is 0. That would make my function undefined. To determine what that value is, I let x minus 2 equal 0, and find out what value of x that makes that 0, and that would be x equals 2. Therefore, I know that my domain for that function is x such that x can be any number, but it cannot equal 2. I also take a look at the range and realize that this is squared. So any value in here, which could be positive or negative for x, when it's squared is going to be positive. And that will, as it gets larger and larger, will reduce this fraction. But it can't get to 0 because 4 divided by infinity will approach 0 but won't get to 0. So y has to be greater than 0, but not equal to. So therefore, this function is going to look something like this. At 2, I'll have an asymptote. In other words, it's not allowed to hit there. My graph's not allowed to hit there. And then it will look something like this. That's the graph of this function. You can verify that using your calculator. Now what I need to do is to find the inverse. F of x is going to be y. And that's going to be 4 over x minus 2 squared. Switch my x and y's. That's going to be x equals 4 over y minus 2 squared. Multiply both sides by y minus 2 squared gives me x times y minus 2 squared equals 4. Divide by x, y minus 2 squared equals 4 over x. Take the square root of both sides. Y minus 2 equals plus or minus the square root of 4 over x, and then add 2. So y equals 2 plus or minus the square root of 4 over x. And that is the inverse of f. Now we need to determine the domain and range. The domain, or my x values, I can see that x cannot equal 0. It also can't be negative because that would give me a negative radicand. So I know that my domain has to be x greater than 0, which was exactly my range of my original function. My range, if I substituted a 2 in for y. I would subtract 2 on both sides. I'd get 0. Square both sides. I get 0 equals 4 over x. Multiply by x on both sides. I get 0 equals 4, which is not possible. Therefore, y cannot equal 2. Again, that's exactly what my domain is for my original function. I also know that if I did graph this, it would look something like this. At 2, it has an asymptote there, and my graph would look similar to this. We can use the vertical line test to determine if that's a function. And we can see that the vertical line test would fail, and this is not a function. In our last example, we have f of x equals 2 over the square root of x. I still need to determine the inverse of this function. I need to find the domain of range of the function and its inverse and determine if the inverse is a function. Let's start with the domain of the function. I have a square root in my denominator. Since x is in the denominator, I know it can't equal 0 because it will be undefined. I also know that any x value that is negative will make this an imaginary number, which will also not work on my graph. So therefore, x must be greater than 0. My range, or y values, any number I plug in here and get out of my square root, in this case, is going to be positive. Since it's going to be positive and the numerator is positive, my y values will also be positive. So y must be greater than 0. And since I'm getting a real number out of my denominator, I'll never get y equal to 0. Actually, if I graph this on a calculator, I would get something that looks like this. And I do know that I have an identity function that will map the reflection. Let's determine the inverse. I'm going to substitute in y for f of x, and that gives me 2 over the square root of x. Switching my x and y's, x equals 2 over the square root of y. That gives me x square roots of y when I multiply by the square root of y on both sides. That equals 2. Divide by x, the square root of y equals 2 over x. Square both sides, I get y equals 4 over x squared. If we look at our inverse, I can have values of x that are positive or negative. Our function only dealt with values of the outcome that are positive. So let's restrict this to x values that are greater than 0. Let's determine the domain. Here I have a situation that x squared is the denominator. Again, I cannot have x be 0 because if it does, it makes my inverse undefined. Therefore, x must be greater than 0. I also know that since I've restricted this to be positive plus it's squared, any value going in for x will be positive, and this is a positive 4, so y is also going to be greater than 0. And if I would plug this into a calculator, I would get a function that looks similar to that. And I did state function because if I used the vertical line test, it would pass, and this would be a function. What I did is restrict this to the right side of the y-axis, or x greater than 0, because if I actually graphed this using the entire x-axis, I would have an asymptote at 0, and I would also have those sets of points.